All right, so welcome everybody. I really want to thank all of our guests here, Jocelyn, Bruce, and Kevin, for the presentations here, especially Jocelyn, who agreed to do this talk with us for all the Costa Rica students and, well, Central American students. And we'll start with a presentation for the book, The Costa Rica Space Directory by Bruce James Callow and Kevin Sanchez. Bruce is a communication consultant, an educator and artist, and he's also the author of the book To the Stars, Costa Rica and NASA, and Intrépidas in Ciencia y Tecnología. And Kevin Sanchez is an industrial engineering student at the Universidad of Costa Rica and currently collaborates in organizations such as TechSpace, Project Polaris, and volunteers in Asteria Space and Satellites. And of course, Jocelyn Burnell, who is an astrophysicist that co-discovered the first pulsar radio signal in 1967. And she's one of the most distinguished scientists in the UK and has received numerous prizes and awards. And she has also served as president and interim president of the Royal Astronomical Society. So thank you for being here, and we'll let Kevin do his introduction, please.
Well, thank you, Mauricio. And well, good morning, good afternoon, or good evening, wherever you are. Thanks for being here. As Mauricio said, I'm Kevin Sanchez, the co-author of this book called Costa Rica Space Directory. So first of all, the Costa Rica Space Directory, it's like a compilation of information, contact sites, activities, projects, and opportunities offered by all of the organizations that are working on this space industry here in Costa Rica, including some international collaboration regarding, well, we hope that this will be a good tool for example, the new Costa Rican Space Agency, and to have all this detailed information in one online book. And of course, it would be a nice tool for all of these organizations to know the other information, the work, the activities of all these groups and institutions, to have a better teamwork, so make more collaborations. And of course, we have like 22 organizations in the book, detailed in 103 pages, and of course our nonprofit organizations like university student groups or formal organizations like startups or government institutions. So in the following slide, we will find the logos of all the organizations in the book. So I will be mentioning everyone, so you can find all of the detailed information in the ebook. So beginning with Academia Nacional de Ciencias de Costa Rica, Arastra Rocket Company, AREX as Aerospace Research and Exploration Company, Aerialytics, ACAE, Alphacen, Grupo de Ingeniería Aeroespacial, CINESPA, Centro de Investigaciones Espaciales, CETEC Lab, el Clúster Aeroespacial de Costa Rica, la Comisión Aeroespacial del CEFIA, el International NASA Space Apps Challenge, TICO Sonde, TechSpace, SWICE, Society of Women in Space Exploration, Space Generation Advisory Council, LEA Labs, Orbital Space Technologies, 9Hub, of course, MISID, Cientech, and Women in Aerospace Costa Rica. So with all of this information in this page, I present all the team in charge of this incredible project. Of course, here we have the well-known Bruce James Callow, as Mauricio said, author of many other books. In this case, well, it's me, Kevin Sanchez, and of course, right, we see Claudia Rojas. She was in charge of all the graphic design of this ebook. And finally, of course, to not take more minutes and time about it, we can see the links where we can find this online and free book in this website. So I will share you the link in the chat. So very soon, of course, we will publish this online ebook in Amazon too, in a Spanish and English version. So I think that this will be all of this project. Thank you so much for your attention. And of course, we hope that this information will be useful for all of the organizations and all the enthusiastic people in Costa Rica and other countries related to the space industry. So thank you so much.
All right, thanks, Kevin. So now we can start with Jocelyn, Dr. Jocelyn Burnell talk. So again, thanks for agreeing to do this with us. I know personally that you're a great inspiration to many students and professionals here in our region. So the floor is yours, and thank you again for doing this. I think you're muted there.
I think Jocelyn's still muted.
Yes.
Is there any assistance we can give Jocelyn, Mauricio?
Okay, I've done it now at last.
There you go.
Sorry about that delay.
No worries.
Can you still see my slide?
No, you'll have to share again.
Right. Slideshow. From the beginning. Is that better? Can you see that?
We can see.
You you cannot see.
Nope.
Oh. Slideshow from the beginning. Is that better?
Yep.
That's working.
No, not yet.
Oh dear. So start slideshow from the beginning. Is that working?
No, we cannot see your slides.
Jocelyn, if you can just double check your share, maybe share again
On Zoom.
sometimes.
Yeah. I may have to.
Don't worry, we'll get to, we've got lots of time.
So I go in there, I share screen. Right.
This has happened to me more times than I can remember.
That one. Share.
There you
Screen
go.
sharing.
Yeah, there
It's
you go.
coming.
Let's see now if we can manage a slideshow.
Yeah,
Okay.
that's perfect.
Good. So thank you very much for the opportunity to be with you. Apologies for the delay getting going, but I think we're now okay. So I was asked to talk about the discovery of pulsars. So I'll start by saying a little bit about radio astronomy. I'll then say a bit about quasars. I'll talk about being in Cambridge in the United Kingdom and the discovery of pulsars, and a few words about what pulsars are. So this is the full electromagnetic spectrum. Here is the bit that our eyes can see, the visible spectrum. To the right of that, we have things like ultraviolet, X-rays, gamma rays. They're all the same phenomenon. It's just our eyes don't respond to them. And going from the red end of the spectrum, we have infrared, millimeter, and radio. And so I'm talking about this part of the spectrum here, the radio spectrum. So radio astronomy started in the 1940s at the end of the World War. This is one of the first really big radio telescopes. It's at Jodrell Bank in England, and it's photographed with a lovely setting sun. They knew during the war that the sun gave out radio waves. What's happening? They knew during the war that the sun gave radio waves. They weren't sure if there was anything else that did, but when they turned their acquired radio equipment to the sky, they found lots of other radio sources, some of which were really remarkably strong. And they were puzzled because when they asked the optical astronomers what was there, the optical astronomer said, well, it's sort of like a star, but it's not any kind of star that we have ever seen before. And these new sources became known as quasi-stellar radio sources, or quasar for short. So quasars were some of the first radio sources found. Trouble started, or puzzlement started, when the optical astronomers got some spectra of those curious star-like things and found that they had large redshift, which meant they were very, very distant. But these things are quite strong. If they're very distant, they should be faint, but they're strong. So they were a very big puzzle for a while. I'm going to jump now to talk about my path into this story. This is a map of the British Isles. I started life at number 1 in the north of Ireland. I had some of my schooling at number 2 in the north of England. And I went to university in Glasgow in Scotland to do my bachelor's degree. And you can perhaps also see that those first 3 places all lie in the mountainous part of Britain, generally speaking, rather poorer and definitely more mountainous. The south and east around London was the rich part of the country where there was good flat land. Having done my PhD in my bachelor's degree in Glasgow, I then moved south. Sorry, I'm having trouble controlling my screen. I moved south, and I've lost the cursor. Brilliant. I moved south to number 4, which is Cambridge. And you can see that this is in the affluent southeast of the country. And when I got to Cambridge, I found there were very few women. I found that a lot of the young men seemed to be very, very clever, quite keen to tell you they were very, very clever, and quite sure of their right to be there. And I found this quite daunting. I'm sure in Costa Rica, you do not have gradients in the country like this, but in Britain, I think people who live in the south and east would see themselves as the ultimate civilized people, and folk from the north and west were savages, uncouth savages. So I was an uncouth savage arriving in this very civilized part of the country. And it was quite scary, quite daunting. When I got there, I felt everyone was very clever, that I wasn't nearly so clever myself. I felt they'd made a mistake admitting me. I reckoned they would discover their mistake and throw me out. It turns out now that we're all a bit wiser, that this is classic, absolutely typical imposter syndrome. You feel an imposter. You feel you do not belong there. Now that I work in Oxford, I'm very much aware that some students coming to Oxford can feel like I felt when I went to Cambridge. And we learn to look out for these students, because if we don't notice them, they will run away. They will go home. They'll say, I'd better leave before they throw me out. And within a few days of their starting at Oxford or Cambridge, they've gone away home. So this is called imposter syndrome. At that time, we didn't recognize it, we didn't name it, but with hindsight, I can see that that's what I was suffering. However, I had had quite a battle to get to Cambridge, to get to do a PhD in radio astronomy. And I was not going to walk away. Sure, they might throw me out, but until they threw me out, I would work my very hardest, so that when they threw me out, I'd know that I had done my best. I just wasn't bright enough for Cambridge. So I was working very hard. In the first week in Cambridge, the new radio astronomy graduate students were given a set of tools each. This is my set of tools. I still have them. And you can see they're not delicate electronics tools. These are full-size, heavy-duty working tools. Because I was going to be doing a lot of wire working with wires. I spent the first 2 years as one of a group of 6 people building a radio telescope. It was quite a big radio telescope. Its area was like 57 tennis courts. And it took 6 of us 2 years to build it. This particular photograph shows me at work, sitting down in the front with my technical assistant, Don. My particular job was all the cables and connectors. And here we are checking that the connectors that I have put on are indeed connecting. This is the finished radio telescope. It took up 1.8 hectares. That's like 57 tennis courts. It worked at 81.5 megahertz. There's a lot of copper wire in this telescope. Those are the actual antennae. The wooden posts are not actually electrical. Their job is to keep the antennae up above the wet grass, because that grass underneath can grow quite tall. And if wet grass touches bare wires, it gives an electrical short. There were almost 200 kilometers of wire and cable in that radio telescope, and it worked at 81.5 megahertz. Our receiver used vacuum tubes, what we call valves. I had used transistors in my undergraduate project, and I said when I came to Cambridge, why don't you use transistors? Oh, transistors are noisy. Oh, transistors are unreliable. We use valves, vacuum tubes. They did ultimately change, but it was still vacuum tubes just then. Now, the project was to find more of these quasars. Quasars are very, very compact objects. And this is what happens when you have a signal from a compact object like a quasar traveling down to a radio telescope on Earth. Oops. But having to go through the solar wind, the plasma that comes out from the sun. That plasma is not smooth. It has clouds with increased density. And when a radio wave comes down, some of the radio wave comes through a cloud, some of the radio wave then gets diffracted. And as the clouds go past, what you pick up on the ground is a signal that keeps changing in brightness. This is called scintillation. In this case, interplanetary scintillation, because this is part of the solar wind moving between the planets and between the sun and the planets. If you have a more ordinary radio source, like a radio galaxy, it is much more extended, and you'll see radio waves that come through clouds and through the gaps in the clouds all at the same time. And the clouds blowing past do not cause this same scintillation. For a radio galaxy, the signal would be something like that, fairly steady. So to find the quasars, you look for a radio signal that scintillates, that bounces up and down like this. It's a bit like what you see at the bottom of a swimming pool. It's not a perfect physics analogy, but if you imagine lying on the bottom of this pool and looking upwards, then as the wind blows the ripples past, you see light and dark and light and dark and light and dark and light and dark. It scintillates. So it's a bit the same sort of phenomenon. Now, Martin Schmidt, it was, Dutchman working in California, who got the first spectrum of a quasar. It was the spectrum of 3C273. And he was very puzzled by it for a while and was finally forced to admit that it was a hydrogen spectrum with a large red shift. A large red shift means the thing is moving away from us at a large speed, which in cosmology means it's at a large distance. And yet it was still bright in spite of being at a large distance. A colleague of his was working on the spectrum of another quasar, and Martin went to his colleague's office. The colleague was busy writing a paper trying to explain why his quasar was made of tellurium, because tellurium was the only thing that had a spectrum even remotely like the spectrum he was seeing. And Martin says, "Do you think your spectrum could be hydrogen with a large redshift?" "Oh, you're right, but it is a large redshift." In fact, it was even larger redshift than the spectrum Martin had. So they had two of these curious objects at very large distances, which meant they had to be really, really powerful because they looked bright. They were reckoned to be about 3 billion light years away, but they had an intensity like a million suns. Martin was quite shocked by this discovery. When he went home from the office that night, he told his wife, "Something terrible happened at the office today." I don't know what his wife thought he was going to talk about. She was probably a little bit relieved when he explained about their discovery. So to go back to my project, there were only about 20 quasars known at that stage, and we really needed to find more. Quasars were subject to a sort of twinkling, changes in brightness or scintillation, because as the signal came to us through the solar wind, through the moving solar wind, they changed brightness. And as I said earlier, broader radio galaxies did not twinkle, did not scintillate. So if I observed with a short time constant so that I did not smooth out the fluctuations, the twinkling, then there was a neat way of picking out the quasars. And having spent 2 years helping build the radio telescope, I was then in charge of it for the next 6 months. I had to debug it, get it working, but actually it worked very well. And I spent the first 6 months of its life using it. And I'm pleased to say that during that 6 months, I found about 180 more quasars. So I got the number of quasars up from 20 to 200. So that was a good piece of work. But as you know, something else happened as well. At that time, the University of Cambridge had one computer. It had less memory than your laptop. It was made with vacuum tubes and it took up a whole room. And very few people could have time on that computer, and we did not. So my data came out on paper charts. And in this picture, you can see me analyzing some of the paper chart. I got 30 meters of paper chart every day. I scanned the sky every 4 days. I took 4 days to scan the sky. So that's 120 meters for one sky scan. And after 6 months, I had 5¼ kilometers of paper. It was a lot of paper. I found quasars, lots of quasars. Unfortunately, I also got quite a lot of interference. It's a very big radio telescope. It's very sensitive. It will pick up sparking thermostats, badly suppressed cars, arc welders, anything that gives a spark will cause interference. At that time, cars, even a car driving down the local road could cause interference. My telescope could see a car driving down a local road. So I got used to identifying this radio interference of various sorts, as well as the quasars. This little bit of the graph paper, it was actually the first observation of a pulsar, but we didn't know at that stage what we had. It would be several months more before we understood what we had. But in this graph, you can see a signal marked CP 1919. That's the first pulsar, and another bit of signal marked interference. You'll see the two look a bit different. On the interference signal, you can see chart paper between the spikes, whereas at least on some of the pulsar signal, you can't. And they also look different because the interference signal, the spikes go up and down, whereas on CP 1919, they really just go up. So the two signals look different. And in making this sort of comparison I've just done, you're actually doing a Fourier analysis. You're asking what frequencies are present. Lower frequencies in the interference, higher frequencies in the pulsar. What amplitudes are present? In the interference signal, you have positive and negative amplitudes. In the pulsar signal, you've really just got positive amplitudes. So that's Fourier analysis. What amplitudes and frequencies are present in your signal? So this signal didn't look like a scintillating quasar and didn't look like interference. And the first few times I saw it, I logged it with a question mark. And it wasn't always there either. But after a bit, my brain said, "You've seen something like this before, haven't you?" When I came across one of these on the chart I was analyzing. "You've seen something like this before, haven't you? You've seen something like this before from this bit of sky, haven't you?" And then it's easy. I'm scanning the sky in declination strips. I'm filing the rolls of chart paper in shoeboxes labeled with the declination. So I go get out the shoebox that has all the previous observations of this declination and lay the charts out on the floor. You need a lot of floor space, but the students were working in an attic and there was plenty of floor space. So I laid the charts out, lined them up by right ascension, and could see, yep, that's the first one that I saw. I saw that one, I marked it with a question mark. Wasn't there, it wasn't there. Think I missed that one. Don't think I noticed that. Wasn't there, it wasn't there. Yeah, I noticed that next one, and here's this one. And look, they're all at the same right ascension. They're all from the same part of the sky. It actually was a very tiny signal, but because I was so sure I was going to be thrown out and was being 100% careful, I noticed it. The signal occupied about 10 parts in a million of the chart paper. I showed this to my supervisor, who said, yeah, very interesting, but we can't see what's going on because that signal is all confined, compressed into 0.5 centimeter, 5 millimeters. We need an enlargement. And with this kind of technology, the way you get an enlargement is to run the pen faster, run the paper faster under the pen, and it all gets spread out. But I couldn't do that permanently because it would get through a roll of paper in 20 minutes. And guess who would be living at the observatory, putting a fresh roll of paper into the chart recorder every 20 minutes, day and night? No. What the graduate student has to do is to go out to the observatory shortly before the telescope will observe this bit of sky. Switch to a faster speed for the recording, let it run till that bit of sky is passed and revert to normal. And I did it for a month, and I made high-speed recordings of receiver noise, and my thesis advisor was furious. It's some kind of flare star, it's been and gone and done it, and you've missed it. It's always the graduate student's fault. And finally, one day I got it. The labeling has been added afterwards, but the bottom trace is 1 second time marks, and the upper trace is the signal that I got in that first day. And you can see there are pulses, equally spaced at about 1 1/3 seconds. And even where the pulses go weak, like under the labeling LGM1, they come back again on beat. It keeps its beat. So I've got something that's pulsing at 1 1/3 seconds. My thesis advisor did not believe me. He thought I'd got the wires crossed or something. But next day he came out to the observatory, and fortunately for me, it did it again. And the pulse period was the same, and my supervisor saw it with his own eyes. And we quickly established that the pulse period was the same as on the previous day. So this thing had been keeping the beat for 24 hours. Something that can keep a beat has big reserves of energy, so it's big. But the pulses are quite steep, which means it's small. So it's big and it's small. Aha. Not very clear. I was told to keep observing this, which I did, and we quickly established that it kept its beat very, very well. First thought was we had picked up some kind of interference, but this interference is moving with the stars. It keeps sidereal time. It keeps to the 23-hour, 56-minute day. Well, it's some kind of faulty equipment. Jocelyn has wired something up wrong. So we asked a colleague and his graduate student to see if they could pick up the signal. They had their own telescope and their own receiver, but it also worked at 81.5 megahertz. And they managed to pick up the signal. So Jocelyn hasn't wired the radio telescope up wrong. But what is it? We quickly established that it was keeping an accurate pulse period. It was not getting tired, which means it's big reserves of energy. But because the pulses are short and steep, it has to be small. So it's small and it's big. Aha, not very clear. A colleague managed to get a dispersion measurement. He took two receivers. He tuned one up in frequency a little bit and one down in frequency a little bit. As a radio signal travels through an environment with electrical charges, free electrons, for instance, the higher frequency waves can travel faster than the lower frequency waves. And the time difference, or the difference between the time it takes the high frequency waves and the time it takes the low frequency waves, is determined by how many electrons there are, how many electrons that wave has traveled past. And by measuring the time difference between his higher frequency and lower frequency signal, and making a guess at how many electrons there were in outer space, he was able to establish that it was way out in space, beyond the sun and the planets, but within the Milky Way, about 200 light years away, probably. Tony thought we ought to check and see if it was intelligent life, little green men. He argued that if they were little green men, they would be on a planet that went round their sun. And some of the time that planet would be coming towards us, and some of the time that planet would be moving away from us, and we should see Doppler shifts on the pulse period. So Jocelyn, please keep making these high-speed recordings so as we can look for fluctuations in the period of the pulses. Well, we did actually find a Doppler effect, but it was due to the motion of the Earth around the sun, because Doppler effect works for the observer as well as the source. But having taken out the effect of us orbiting the sun, we found no other Doppler effect. So we proved that the Earth went around the sun, but otherwise weren't making fantastic progress. And then I found a second and a third and a fourth. And it really began to look like we found a new population of something in our galaxy. The name Pulsar was created by a journalist. His name was Anthony Michaelis, and he works for a very conservative newspaper in Britain called the Daily Telegraph. And he asked us what we were going to call them. And we'd given some thought to this. Should we call them pulsating radio sources or pulsed radio sources? And we opted for pulsed because, we opted for pulsating because pulsed might suggest somebody or something was making the pulses. In other words, little green men. So when he said, what are we going to call them? We said, oh, we thought about that. Pulsating radio sources. He said, no. You need a short name, a bit like quasar. What about pulsar? And pulsars they became, and they've been known as pulsars ever since. So in case some of you haven't met pulsars, here's just a brief summary of what they are. They're very small stars. They're very massive stars, so they're extremely dense. Actually, what we sometimes call a neutron star. And they spin, in this case, about a vertical axis. They have a very strong magnetic field, which is inclined to the spin axis. And through some very complicated physics, a radio beam comes out at each of these poles and sweeps around the sky as the star spins. These are the two beams. If a beam shines in our face, we see it, we don't. We see it, we don't. We see it, we don't. There'll be many orientated where we do not see either beam. We have one or two where we see both beams, but mostly we only see one. It's a bit like a lighthouse for guiding ships at sea, shining a beam round the horizon. They're small, they are about 10 kilometers radius. They're very dense because they have the same mass as a star like the sun, and they're rich in neutrons, so they're known as neutron stars. They've got very strong gravitational fields because there's a lot of mass in a small volume. They also have very strong electric and magnetic fields, and they're rapidly spinning. So the physics of these things is really very difficult. They're probably formed when a massive star, more than 10 times the mass of our sun, explodes at the end of its life, what's called a supernova. In the explosion, the core of the star gets compressed and kicked against and shrunk, and so forms one of these very compact neutron stars. And it seems to be that they're mostly observed as these pulsed radio emitting objects, which became known as pulsars. I'm not sure if this soundtrack will work. Let's see. That was an audio recording of a pulsar. So today, there's a lot known, and I think there's a typo here. I don't think it's 30,000. I've got an extra zero in there, 3,000. They're primarily radio objects. Some are seen in X-rays and gamma rays. About 20 are seen in the visible, about 100 in X-rays, and interestingly, even more, 200 in gamma rays. Of the 3,000, 10% are in binaries. There is one pulsar binary. There is one triple system. And amazingly, there are a few with planets. You'd think the explosion that created, the supernova explosion that created the pulsar would send the planets away, but apparently not. And there's maybe about 100,000 pulsars in the galaxy, and presumably in other galaxies, but we've not seen any in other galaxies yet. That requires a lot more sensitivity. So this is an example of a supernova. This is part of the Large Magellanic Cloud. Lots of hydrogen gas, lots of stars, one inconspicuous star identified with an arrow. Look at that corner of the photograph. It's gone supernova. This was supernova 1987A. And the arrow was added after the photograph was taken. There are not arrows in the sky telling us where to look. It is not so easy. We have expected there to be a pulsar in this. We have never found a pulsar, but we have evidence of something hot at the core here. It's heating up some carbon monoxide gas. So there probably is a neutron star there, but we're not seeing the pulsations. Perhaps the most famous one is the Crab Nebula, Messier 1. This was known to have a supernova explosion about 1,000 years ago. And there was a big puzzle as to why this kept shining so brightly. It's 1,000 years old. It should be fading. It was not fading. We now know that there is a pulsar. Where's my app? There's a pulsar about there. And it's energy from the pulsar that's keeping this nebula shining. There are several interesting stories about how pulsars were nearly discovered, which I'm going to tell you briefly. It's 1957. We are in Texas at the McDonald Observatory. And McDonald, when he gave the money, said, the telescope must be open to the public one night every month. It is that night. There's a student or new graduate called Elliott Moore who was assisting that night. He was an intern. And the telescope is set on that curious star in the center of the Crab Nebula. A young woman steps up to the telescope and says, that star's flashing. And they talked about scintillation. She said, no, I know about scintillation. My job is to fly newly built aircraft from the manufacturer to the customer. I fly at night. I know about scintillation. That star's flashing. Elliott Moore reported that nobody followed up. The Crab Nebula pulsar does now, we now know, flash in the optical. It flashes at 50 hertz. Some people can see, 30 hertz. Some people can see 30 hertz because Canada used to have its main power supply at 30 hertz. And some people, especially young women, could see the flashing. Elliott Moore thinks that young female visitor saw the Crab pulsar flashing in 1957, but nobody followed up. A second story about the same pulsar. The Australians in June 2007 suddenly get an email from a gentleman called Charles Schistler. He's in this photograph. He's the furthest face in the photograph. He explains that he was a United States citizen. He had to do military service. He was posted to a radar station in Alaska, looking for Russian missiles coming in. When things were quiet, they were allowed to play around with the equipment. And one day he was playing around with the equipment, not the transmitter, just the receiving equipment, and picked up some flashing signals, which were not incoming missiles. He'd done an astronomy course at college. He knew about right ascension and declination. He estimated the right ascension and declination of the 14 pulsing sources he found, and illegally probably took that note away with him. He has just discovered the online pulsar catalogue that the Australians keep. And he's discovered that several of his pulsing sources are pulsars in that catalogue. And he writes to the Australians in great excitement. They did check him out. They believe he was genuine. Another example of how the Crab pulsar was almost discovered. Sue Simpkin. Sue Simpkin started life in Canada. She started life in Canada when their power supply was 50 hertz. She knows she was one of the young women who could see 50 hertz because through her childhood, she was driven mad by all the lights flashing, the television flashing, and so on. She's now an astronomer. She's going to take an ultraviolet spectrum, and Lo Vulture from the Netherlands asks her to take an ultraviolet spectrum of that funny star in the middle of the Crab Nebula. She does so. She says the spectrum's dull, but she sees a rapid flickering, or as if there were waves going out from it. Lo Vulture says it couldn't be. But when the Crab pulsar was discovered and discovered that it flashed in the optical, he was man enough to say, "You must have seen it, Sue," and I didn't believe you. And the final example is a radio survey to map using the largest available telescopes to map the sky at 408 megahertz. They've been getting time on big telescopes where they could. They're nearly finished. They have some gaps in their map and they're busy filling them in. And early one morning, about 3 o'clock in the morning, they're using pen recorders. This is old technology. One of the pen recorders did not behave well. And at 3 o'clock in the morning, that pen recorder started going weep, 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 weep. And the observer did what we always do. He cursed it, and then he thumped like that, the pen recorder. And it stopped going weep, 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 and went back to normal. So he said, oh, good, put on his coat and went home to bed. And he did not make any note in the logbook. If he had made a note in the logbook, he could have claimed prior discovery of the pulsar 0329 plus 54. So this is why people keep telling you to use your lab notebook thoroughly. Do write things in your lab notebook. You never know what that funny behavior is. So I think I have said all of that. How did pulsars get discovered when they did? Well, we had our own telescope and our own receiver, and I made it my job to understand how they behaved. I was a graduate student, a research student, so I've got time, space to follow up anomalies. But I also have this imposter syndrome. They've made a mistake admitting me. They're going to throw me out when they discover. And I'm working my very hardest to try not to be thrown out. This was one of the first surveys of the radio sky with a short time constant. Indeed, we didn't actually know of anybody else doing similar work. But the observing frequency we used, 81.5 megahertz, is not the optimum frequency for doing pulsar work. And the first pulsar was not the strongest pulsar we ever found. So we were a bit lucky. We had a good address. It was a reputable laboratory. So when we announced this crazy discovery, people were inclined to believe us. Finding pulsars was not one of the objectives, one of the targets of the program. And in Britain now, your research is graded by how well you have achieved the targets you said you would achieve. This wasn't one of the targets. How would we have been marked these days? And if we had computerized the search, if we'd used computers, would we have told them to look for pulsars? Because we did not know such a thing existed. Interestingly, just a few months before the discovery of pulsars, Franco Puccini had been wondering about how the Crab Nebula was kept shining, and he postulated that there might be a neutron star in it with a large magnetic field, and that the magnetic field was inclined to the spin axis, like you saw in the animation I showed you, and that this would produce magnetic dipole radiation at the rotation period, which could not escape the plasma, and the energy that it dumped would keep the nebula shining. It was a speculative paper. Within 6 months, he'd been proved right. I finish with a photograph of the Pulsar group in Oxford, where I work. Thank you for your attention and your interest. Thank you very much.
Thank you, Jocelyn, for the great talk and the great insight. And one thing I really like is how you tell your story every time you give a talk. And yes, that's something usually you only read on books, but it's nice to hear it from you.
Thank
you. I believe we have time for a couple of questions.
Mm-hmm.
So Maria Rene Mesa says, what are some unanswered questions about pulsars?
There are quite a few unanswered questions. There are theoretical questions about how exactly the radiation is produced. We still haven't explained that because it's very, very complicated because of large electric fields, large magnetic fields, high speeds of rotation, high density. It's very difficult physics. So that's not really been properly explained yet. We still don't know how many pulsars or neutron stars there are. We can only see a pulsar, we can only have a chance of seeing a pulsar if its beam shines on the Earth. So we're unclear how many there are and how common they are. And we're unclear also how they evolve. They probably start spinning very fast and gradually slow, and then sort of die off, they get so slow. But there's more work to be done on that as well. So quite a few areas of work to be done.
Quite a lot of questions there.
Mm-hmm.
Another question is from Amber Alinsky and says, how have you gotten through your imposter syndrome?
I gradually got braver as I found I was managing okay. And having the discovery of pulsars, so to speak, under my belt, behind me in my record, helps a lot. But I've also had to change wavelength a lot because my husband kept moving jobs. So each time you start in a new wavelength, you feel very stupid. You have a lot of learning to do, but you can do it.
Thank you. And there's one last comment in here from Jose Tecun. He says, I watched a documentary they made about you in the New York Times, and his question is, how do astronomers know how to differentiate between pulsars with both poles pointing towards Earth and the ones only with one pole pointing towards the Earth?
Yeah, I think we only know of one or two that have both poles pointing to the Earth. And actually, they aren't pointing exactly to the Earth. So you get a slightly stronger pulse followed by a slightly weaker pulse. So it goes strong, weak, strong, weak, strong, weak, strong, weak. And you reckon that's because you're seeing both poles, but not quite pole on.
Thank you. So I believe there are no more questions, and we would really like to thank you again for the great talk and for always being an inspiration and always being a figure for us.
Thank you very much. It's been good to be with you. Good wishes to all of you too. Thank you very much.
If I might be able to throw one into just before we close, sort of a general question, please. What advice would you give young Costa Rican, budding astronomers, physicists, especially women coming up in this field?
Yeah, well, I think astronomy is a fantastic field to work in. There's a lot happening, a lot of interest, but you do need good physics. So if your physics is good, keep on thinking about it. If you need to strengthen your physics, well, strengthen your physics first, because you do need good physics to do astronomy. But it's a very exciting field. There's so much happening. It's a fantastic field for young people.
Thank you.
All right. Thanks, Bruce. And thanks again, Jocelyn. And we'll
Thank
see
you
you all
much.
on the next one.
Thank you
Bye
very
bye.
much.
Thank you
Take
so
care,
much.
everybody.
Take
Bye-bye.
care.
Thank
Bye
you.
bye.
Bye-bye.
Bye.